Test, test. All right, so welcome back, everybody. So let's continue our tutorial on this overview of SMT, its applications. Again, please interrupt me if you have questions. All right, so yes, so you're here. So we're talking about the theories that we have in SMT, all these different theories that allow you to phrase all these different kinds of problems. Any problem that you can fit in one of these theories, you're going to have a procedure that hopefully it's going to be reasonably efficient to solve it for these ones that we have seen so far, other than floating points, which are tough, but like things tend to behave well. So I mentioned before the theory of algebraic data types. This is a very general theory that allows you to model arbitrary data types that follow the properties that you expect of algebraic data types. They are cyclic, like they must have values chosen across its constructors that are all distinct, and so on and so forth. So you can have things like any data structure you can model using this kind of stuff generally. Some of them you have dedicated theories for example, as we saw like with arrays, for example. But strings we're going to see in a bit also. But this gives you a general procedure to reason about data structures that you may have in your program. And the way that solvers generally solve these problems, again, is by reasoning about equality, reasoning about like these things as function with the extra properties that you have here for these constructors and selectors. We're not going to do an example directly in the interest of time, but like when I upload the material, like there's going to be also an example of how you would write like a Python program to do this. Oh, I can just show actually, like I have already it. Yes, so this is a problem that you would create your data type here. It's a tree. And then you would have your properties and so on. So like in the same way that you have these functionalities for the other theories, you're also going to have for data types. But I'm not going to go through these in detail. It suffices to say that this is also a very useful theory to combine with other ones to be able to model data structures. So I wanted to talk about strings and regular expression a little bit, given the high interest like nowadays in verification, involving strings, involving sequences, it's just generalization of strings, regular expressions as well. And just to give you a flavor of like how intense this theory is, I mean, you are reasoning about like a concatenation of characters, right? Like, but there is a lot that algebraically goes into problems involving this theory. So say, let's do this example. Can we have a string with at most 3 characters that contains the string ATVA, right? So in principle, we should not expect this to be possible, right? Because this has more than 3 characters. But I can write this Python program here that is going to create a solver for this logic. So this S stands for strings, and we also have linear integer arithmetic here. This is because we're also going to reason about length. And then when you're reasoning about length, you have to do arithmetic. And then I have this string variable, okay? And the constraints I'm going to add here, as written like in the example, is that the length of x has to be at most 3. Okay, so it cannot have more than 3 characters. At the same time, I want to force it to contain this string here. So this I should expect to be unsatisfiable. And it is unsatisfiable. And it is generating a proof. It took a while because the proof is long. And the reason the proof is long is because the procedure to solve problems in the theory of strings involves reasoning about many reasoning elements. And therefore, like this goes on, right? And it cannot display everything. It has hundreds and hundreds of steps of reasoning to be able to determine the unsatisfiability of these 2 things here. That you could try to solve more efficiently in a different way if you had a notion of like computing and rewriting and so on, but like to have a general reasoning procedure, you do have to consider a lot for these kinds of data types. But being able to reason about strings do allow a number of interesting applications to be built on top of SMT solvers, as has recent interest shown. Okay. And there are many different approaches that, yes?
Is it possible to kind of making the proof by introducing some form of lemma or something? Because in the current example, if we know that the fact that if two strings stands in a contains relation, then that length is stands in inequality. So that, is it possible to by introducing such lemma to shorten the proof?
Yes, yes, definitely. So this is something that actively happens. So for example, like this is a problem that you would have expected to solve more efficiently, as you just said, right? So what does an SMT solver developer do in such a case? So he would implement a simplification procedure, as we call it, to in certain cases, when you have certain kinds of patterns in your constraints, you would be able to infer a lemma like this one that you described. And this is exactly the case that you have here. If you have a contains of a variable and then a constant here, then you can automatically infer that the length of x has to be greater or equal than 4. And then this would be very simple to show it's unsatisfiable together with this other constraint. It just so happens that this version of CVC5 does not implement this simplification. But this is something that I have a colleague, Andrew Reynolds, who works a lot with string solving, and then I have shown him this example. He was very unhappy with like how long the proof was from CVC5, and he said, oh my God, we should solve this via simplification, exactly like this. So this is the sort of situation that happens a lot in these complex theories, that you have sort of blind spots for simple reasoning. And this happens very often, like that a user is going to report, I have this simple problem that is not solved efficiently. And then the solver developer is going to identify that there is a pattern of a simplification that could be done to shorten the proof.
Yes. So this is slightly meta question. One is that what are these proofs meant for? Are they meant to be machine checkable or human readable? And if they could be made human readable using like large language models are there, and the question is there any way you can make this more understandable to humans, even if it's a really long proof?
Right. So it is meant to be machine checkable, and some people, like me, would very much like to make them understandable. So I have started playing with like visualization. So CVC5, for example, it can. I don't think I'll be able to do this live. Like, yes, it. Okay, so I mean this is improvement. So like it can generate like a dot file that maybe this will work. I mean, since you asked, like T talks examples. Will this work? I don't know. So I mean, to say what I'm trying to do. So this is a visualizer. Oh yes, it worked. I mean, this will not be. How does this work again? Yeah, this is very slow because the proof has 5,600 nodes. But this is a toy visualizer I had a student building that can read in a dot file that CVC5 can generate, and then you could try to visualize, but it's very difficult because these proofs can be big, and there is some structure that you can try to infer for it. But for like, let me just try one thing. For this, since it's too big, it is very difficult. But what you there is active research that you can do to try to do this, like to identify components, to generalize, and so on. Maybe large language models is something that you could try, because, I mean, you could build like a big data set out of proofs to try to do something with them, like to, but without a guidance of like what would you be looking for in terms of meaning. But this is something that I think like should certainly be of interest. Oh yes, so this is what I want to show. So like this has already some sort of like abstraction in the proof that you are abstracting some parts of the components. These colors are meant to be different sorts of reasoning that are happening. Here is Boolean reasoning. Here is classification. These parts here mean simplification. These green parts mean theory reasoning. But still, like, it's very big. Like, it gets smaller, but like each one of these things can be very big, but it would be a path to go in this direction. But the original intention of these proofs is to be machine checked. But there is a lot that could be done to maybe get into something more. Okay. All right. So there are many other theories that have been developed like through time in SMT solving, and there are things that you can do with finite sets, for example. People have been interested in transcendental functions. Then this is always going to be motivated by some sorts of like applications, right? If you want to do verification of like zero knowledge proofs, etc., you can use finite fields. Also smart contracts use this, and so on and so forth. So as new applications emerge that can benefit from SMT solvers, people generally do new theories, but why? So one thing I wanted to say also is that many SMT solvers support quantifiers in which you can do your own axiomatization of a theory. Notably, CVC5 and Z3 have good support for them. When you have quantifiers, however, and this is the motivation for in the previous series we'll be focusing on quantifier-free fragments, is that you almost always you get to undecidable fragments, so you can only hope to have incomplete procedures that are not going to behave as well as in the quantifier-free fragments, so users are going to be disappointed. But it does give you a lot of flexibility, and in certain cases you actually need this because there is no way you could have like a theory for every sort of variation of a problem you could have. But what I wanted to show briefly is you could. So this is the problem we were solving with arrays, right? So we had the theory of arrays, we had these stores, and then we had this notation to represent the select, and then the solver could reason about the satisfiability of these constraints. Sorry. I could, however, not use the theory of arrays and do my own axiomatization of how these arbitrary functions that I define, that I have called store and select, over this data type here that is in an interpreted sort array, behave. So I do axioms, which are these quantified formulas. So this is a notation for having like a universal quantification. And what I'm encoding here is exactly the axioms that these functions that represent store and select of arrays should respect. And then if I write like the constraints that I had before, I again would expect this to be unsatisfiable. However, this unsatisfiability is going to be determined not, so it is unsat, right, and then I can get a proof, but this unsatisfiability is determined not by reasoning about the array operators using a dedicated theory, but by using a general procedure to reason about axioms, which in this case CVC5 employs using what is called instantiation. So as we determined before, right, this is supposed to be always true, so this formula would not be unsat, it was sat. However, now that I'm using quantifiers, the result I'm getting is unknown. And the reason is that by default, when CVC5 is solving a problem containing axioms, it's not going to employ a complete procedure, so it is employing one that can fail and often struggles to say that a problem is satisfiable, because it can be harder to build models when you have quantified formulas involved in your problem. But if I did what we had before, which is negate this, and then have like that this is valid, it will also fail. Maybe if I had this option here. No, also fails. Well, pity. It happens. So like we are in an incomplete fragment when you have axioms. This is why you have theories, right? So like, so what I wanted to show is this cycle here, is that this happens a lot. Like you have a new domain that would benefit from an SMT solver because it involves a combination of different kinds of reasoning, but you have no theory for it, so you do an axiomatization, it works well for some examples, then it fails in some things that you would very much expect it to succeed on, so you get very frustrated. And then research happens, you develop a new theory, and then it can be much faster than like this roundabout approach, so to speak, and then that new theory becomes a standard, and then it's gonna show up in talks like this. Yes?
Integration.
So if I understood correctly, you mean like about having the SMT solver a general reasoning procedure for axioms and not have just the theories?
Yeah, just do first order reasoning when you see axioms. I wonder if that would be a better strategy or something is lost.
So this has been tried. So like in Z3, Leo De Mora and Nikolai Bjorner tried this. So they integrated a superposition, which is the state of the art for first order theorem proving in Z3. However, what you have as an issue is that the way the SMT solver works is that the reasoning is stratified. So you have a problem, you abstract it propositionally, you get like a satisfying assignment for the propositional structure of the problem. Then you do theory reasoning to determine if what propositionally has to be true can be true at the level of the theories. So this is how an SMT solver generally performs. So you are doing a lot of work on guesses from the SAT solver. So this is what kills you, because if you have a very expensive reasoning that is based on a guess, then you may spend too many resources on something that cannot be true, and it's going to be very expensive for you to determine, especially if you have a non-terminating procedure to do this, which is the case when you have quantifiers. So it becomes very hard to determine how to interleave. And a general motivation of all of these procedures for doing theory reasoning, and therefore also how quantifiers are handled in SMT, is that you want to, as fast as possible, infer facts that are going to allow you to move on with the search. So the reason why this approach failed when they tried to do this in Z3, and also when other people try to do this in other systems, is that it becomes very, very hard to determine how far you want to go in the first order reasoning versus the guessing that the SAT solver is doing. And this is why in a solver like CVC5 or the approach that is generally used in Z3, it's based on instantiation, where you are not guaranteed to be generating useful facts, but facts that you can derive very fast and that have a reasonable likelihood of being useful.
All right, so there is another, say, approach to implement decision procedures for new theories, which some people have done in the past, for example, for data types in the heap and stuff like that, where you prove for your specific theory bounded model theorems or cutoff theorems, and then giving the formula that you want to prove the satisfiability of, you compute the bound, and then you generate a specific SMT query for that bound that you extracted from the formula. So at the end of the day, you implement a decision procedure for your theory, but there is a lot of handcrafted code that takes you from the input formula into your SMT query. And the answer to the query is very different from the model that the user would expect from the original formula. So you have to write even more code to build something meaningful for the user, which I don't think it fits in your loop somehow. This is what, is there anything interesting to be said about, say, a standard way to implement this cutoff approaches or bounded model theorem approaches?
Yeah, so I must say I'm not very familiar with this approach, nor I'm certain I quite understood Like, but it involved like a translation of your problem to like sort of a general procedure that you would instantiate for the particular rules of the theory and reason on that. Is that what you mean?
Yeah, somehow. So imagine that you have a theory, say, I don't know, a theory of single linked lists in the heap, something like this. And then you prove that in your theory, if you look at the formula and you look at the elements in the formula, you know that if there is a model, there is a model with at most 5 elements.
Ah, okay.
And then based on that information that you extracted with your handcrafted theorem on your theory, for a given formula that you want to prove satisfiability, you compute the bound, and then you generate a specific SMT query for that bound to do the search efficiently.
I see. Yeah, so the terminology we generally use for that is symmetry breaking. So you do an analysis of the formula, you infer a new formula that is equisatisfiable, and then you reason on that formula. So that is an approach that is used a lot, like for certain fragments where people have determined like good symmetry breaking approaches. In SAT, for example, it's something that is even more used, like people do that even more often. If you are interested in, however, keeping that traceability, as you mentioned, then it becomes very problematic because it can be very difficult to, because generally the reason why you can generate that bound depends on the whole formula. So like how you're going to write a justification that is not linear in the size of the formula. But like certainly there are many opportunities because for each theory you can have dedicated symmetry breaking, right? Like there are deep particular ways in which you can do this approach. But like it's certainly an area that has been well explored in some theories, like in EUF, people have good ways of do symmetry breaking when you have only equality and uninterpreted functions. But in other theories, there is more to be done.
But if I could rephrase my question, I would say that SMT solvers are great, but the API is not very friendly if you want to implement this kind of solvers on top. Mm-hmm. But maybe it's a difficult problem.
Yeah, but like it would certainly be interesting to understand like what are the particular ways in which you're trying to do that, and then like explore how to provide better APIs to do this. Cool, thank you. All right, so finally, let's talk about some applications. I mean, in a sense, like each one of these examples you could think of as an application because you are building it directly on the theories. But more specifically, I want to talk about common things that we do in formal methods in general that directly benefit and how we benefit from SMT solving. So, for example, let's consider the bounded model checking problem. So this is when you are interested in determining whether your system, right, contains a set of bad states that is reachable. So what you can do is to encode via an SMT formula that is going to represent like how you have reasoning in your system, like how to do this reachability. So you have to represent the set of states that you have in your system, right? Like as these variables representing the states. And then you can have a set of initial conditions and a relation that marks the transitions in the system. And then what you want to determine is if after a number of operations of the transition relation, then you have or not reached a state that has this bad property. And this is used a lot, like, for example, in hardware verification, like when you want to determine if after a number of cycles, like in your circuit, you have some bad property or not. So you have to encode, like with this formula, the representation of the bad state that you can reach. And then you do the expansion of the number of transitions that you can have, right? So you can have a number of variables representing all the different states that you can have in your problem, and then you just generate a big problem representing all of this reasoning, and then you determine whether that is satisfiable in the theory that you are representing this, right? So notice that like we have this new instantiation of the state variables after each one of the iterations. All right, so Yes, so then bounded model checking is an application that there are different ways in which you can do bounded model checking, right? You can do this encoding into SAT, for example. This has been very successful also, but if you use SMT, then you can reason directly at the level of the theory you have in question without having to encode this into SAT. So we can do like a simple example, which is to consider like whether a given property holds after 10 iterations of this C code that we have here. So we have this loop, right? And I can just unroll it 10 times, and then I want to test whether after 10 times this property holds or not. So the formula that I have to show, to build, is the formula that represents exactly this, right? So I have this set of initial conditions, which is the restrictions on the state before I start doing the unrolling of the loop. Then I have how the state changes after each iteration of the loop. And then finally, I have to test after the iterations I'm interested in, whether the property holds or not. So what I have to do is to encode into SMT the semantics of the operations I have here. And then there are different ways in which you can do this, right? So we are going to use bit vectors because I have these 32 bits integers here to represent the values of these variables. We have this variable here that is a Boolean variable that can assume different values at each state. And then I have this property to be tested at each one of the possible unrollings that I do. And then I have this if then else that represents the way in which the state variables are changing, okay? And then I can, and this is where using something like the Python API becomes very useful, because I can have a programmatic way of generating the formula that corresponds to the n iterations that I can do in this bounded model checking application here, right? So this is exactly what we are going to do. I'm not going to write from scratch the example, because it would be tedious and long. So what I'm going to do is I'm going to open here this Python program and explain to you guys what's happening, okay? And then please stop me if it's not clear. So I'm going to write this BMC function that I'm going to parameterize by how many unrollings I'm going to do. And what this is going to do is the bounded model checking of that program. So I'm going to encode directly the semantics of that program. So I'm going to do for 10. So I have the inputs, right, is this turn variable, which was changing at every iteration of the loop. So I'm just going to create a variable for this guy. I have these A and B, which are bit vectors, because these are machine integers. And then I am going to have here the lines, well, 19 and 20 are here, that are going to be from my state giving me the next value of the variable. Because I have an if then else to determine what is the next value of A or of B. So at each iteration of the loop, intuitively what's happening is that depending on the value of turn, I am either incrementing A or incrementing B, right? So what I'm going to do is to create new variables as this next A and next B here that are going to represent the new iterations that are going to be happening based on these if then else's. And then I have the property that I'm checking, which is that it's this assert here, right? That either A is different from 3 or B is different from 3, which I'm representing here as the negated conjunction that they're both equals to 3. Okay, so these are the elements that I'm going to use to build at each unrolling of the loop new versions of these variables that represent the values that they have in each point of the unrolling. So, okay. So initially I have the A, B, turn, and prop. These are the original things that I have. And then I'm going to create a BV solver, and I'm going to call the solver at each level of the unrolling. So what I'm going to do here is that I'm going to first test the property at each one of these levels until I get to 10. And then if I fail before that, I'm going to determine after how many unrollings I have failed. So I'm going to iterate over the bound. And then I'm going to have some auxiliary functions here that are going to help me to build the formula. So in the initial condition, I know that initially the values of A and B are 0. So when I test the property the first time, this is the values that I should have for these variables, representing that the values of A and B in that point in the unrolling. Otherwise, I am going to build a formula. And how I'm going to do this? So I'm going to have, I had here a prop, right? So this prop is based on A and B. But I'm going to generate new versions of this formula at each iteration. And this is done using this substitute method here, which what it does is that, so this is provided by the CVC5 API. So it gets a formula and replaces the occurrency according to the substitution of what is in the domain of the substitution to its image. So yes, so the next A here is the way to calculate the next value of A. So like in this A at K and B at K and turn at K are going to represent the variations of these variables at each one of the iterations, right? So maybe let's see an example and then I can print the formula as it goes. Because the constraints that I'm going to add is that at each iteration, I'm going to make the next state values of the variables to be equal to what I had before according to the constraints of the code. So this is going to be encoding the transition relation that I have represented in this program, right? And then I'm going to add this to the solver, and then finally I'm going to check the property with that level of the unrolling up to now. So if I do this, I have, I print the constraints. So let's do this with 2 at first. Right, so at first I have that A and B are 0, okay? And then the property that either one of them is different from 3 holds, so the property is not violated. Then I do the first unrolling, and then the formulas that I have in my solver are these are the initial conditions, then this, which hold, and then I create a variable for the next state, right? And then the value that A is going to have after one iteration is going to depend on the value that it had before and on turn, okay? The same thing for B in the next iteration, and then I have tested the property, and then the property did not fail. So if I did this with 3, it would continue to generate new formulas, okay? So note that I had exactly what I had before, but I added the property here, right? Then I generate the new iteration, and I continue. So if I do this until 10, what I have to see is if there is a level in the unrolling in which the property is falsified. And I'm going to, yes, so this is going to fail after a number of iterations, and then I can see here the different values the variables had at each iteration. So this is all done like in that Python code that was generating the formula and also tracing this information such that I could print them. So these are my initial conditions, the property holds, then given that turn was false, right, I was going to increment B, and this is what I have here. So now turn was false, I'm going to increment B again, and so on and so forth. So when I generated the formula, the values of turn were free because this was an input, so it could change arbitrarily. So the question is there a trace in which there is a value, a series of values for turn that allows the increments to happen in a given order that is going to make the property break? So you can generate a series of formulas that represent the test up to X iterations, and then if it does not fail, you're going to generate the next formula, and so on and so forth. Moreover, the way this is done in the solver is such that you are doing here this push and pop of the property. So you are keeping the formula that you had except for adding the property testing. And this is what is called, like in terminology, incremental solving. And then this allows you to keep the reasoning that the solver has done that did not involve the property, such that you do not throw away everything. You are only throwing away what was specific to that iteration, testing the property, and then you continue. Okay? So this is a way that people commonly use SMT solvers. It's to reason about the semantics of problems, of programs, in this case specifically doing bounded model checking by doing like a limited number of unrollings just to see if your property holds. Because I mean, this corresponds to an infinite state system, right? So like you would need to reason in a different way if you wanted to test that a given property that for a program that contains a loop holds. But what is interesting in using these APIs is that you can very directly generate these formulas iteratively and then have all this extra machinery to understand. However, you can also directly generate a script in SMT-lib that contains the same sort of reasoning because it also has the capabilities of doing this incremental push and pop. All right. So let's say that we wanted to do symbolic model checking, which is not when you are interested in a limited number of unrollings, but like considering the full, potentially infinite system. So now you want to check that a property is invariant in a given system, in a program, for example, that for all potential ways in which you can have the behavior of a program, like a given property, always holds. And then we have the same sort of setting in which we can encode formulas in SMT that correspond to the testing that this is the case, to the checking of the satisfiability that, well, the negation of the formula is valid, for example. Well, it's unsatisfiable, so the formula is valid. All right, so we have the same sort of setting for doing the encoding, as we call. So this is the part that is more relevant here, is like how you encode into SMT the solving of such a problem, right? Like this is where a lot of like the usefulness of SMT comes from, is on the understanding of how to generate SMT formulas whose satisfiability correspond to solving interesting problems. So we have the same abstraction of how the system is going to behave, a set of initial conditions, a transition relation, and then a property that you want to show like invariant. So for every potentially reachable state, you want to show that this is the case, right? So like this is complicated because like you have potentially an infinite state system, so how you're going to show this? There are smart things that you can do. So let's consider this example. It's a parametric resettable counter. So what's going on here is very simple. You have these inputs that represent your state, right? So you have a positive and 0, you have a Boolean, and then you have a counter and like a value for n. And then your transition is simply that the value of n is always the same. So this prime here represents the next state. And then the new value of the state of the counter, so the value of the counter the next state, is going to be determined by whether you have reached this n or you had like this r set to reset the counter. So if we think about this, we can see that all the states that we're going to have in the system can be represented like this, right? It's a very simple system. So you have infinitely many instances of this schema depending on n, right? Because the states that you can have here, at the end of the day, you can have like a cyclic behavior, but you have a finite number of states that is bound by n. that you have in this system. So we can think like that this property is indeed like invariant, because in every potential state that you have here, it is the case that C is smaller or equal than n+1. What gets difficult, however, is to prove this. If you want just to show that a given property is invariant, you have to reason about the infinitely many computations that can happen here. So what we generally do is to do something different. Because first, so like I can encode the different elements of this problem using SMT, similarly to as we did before. I have these variables corresponding to the state, right? The values of C, of N, of R, and of N0. I have the initial conditions on C and N. And I have this transition relation that is going to modify the values for the next state. And I have my property. So the way that we generally prove things in this setting is by using inductive reasoning. By thinking of my system as this in an inductive manner, by showing using induction that if I have a property that holds in the initial state and then it's preserved by the transition relation, so it is inductive in that sense, then that property always gonna hold, right? So I can have an induction proof of the invariance of a given property. So what can be problematic about that? What can be problematic is that not all invariants are inductive. In particular, not this invariant. So this invariant is not inductive because it breaks the inductive step. I mean, it's easy enough to do what we are going to do, which is to come up with an inductive invariant that entails this invariant. So I can show that another property is invariant, and that property suffices to show this property. But I cannot show that this property directly is invariant. So there is this roundabout way in which we reason about symbolic model checking when we are doing things in this setting, which is that I have to come up with an inductive invariant that suffices to show the property I'm interested in, okay? So how do I want to do this? Yes, so I have this counterexample here, but I could do this also here. So I have written like this Python program that, ignore this part. So I have here like the encoding into SMT of the elements of that transition system, right? So I have here the variables corresponding to the state. I have written like C underline P to represent the variable for the next state. I have here the initial conditions, which is that C is 1, N is equal to N0. I have added that N0 is bigger than 0 because I do not have natural numbers as a type in SMT. I have only integers if I'm reasoning this logic, and therefore there is generally no logic for natural numbers, so I have to myself add the restriction that the N0 is bigger than 0. Well, actually, yeah. So I have here the transition relation that encodes what I had here, right? Exactly this. And finally, I have the property. So I have written this simple program here that generates a formula based on the arguments that I give to it, such that I don't have to write the 2 times the property for the non-primed and primed variables. And then I can try to prove both the properties that are required for this invariant to be inductive. And if I try to do this, it's going to fail. Right. So it fails in a similar manner to what I had here, but not quite. Can you see any issue with what I did so far? Although I did go a bit fast, so it can be more difficult to see. Wait, I'm lost. Here, yeah. So this is what we did. By the way, this prove command, what it does is that it, by itself, it creates an SMT solver of the appropriate logic depending on the constraints that you have, and then it's going to invoke the satisfiability test on the negation of what you asked it to prove. So it's a shorthand for assert, then check satisfiability. Assert the negation and check satisfiability. Yes, so like, so I noticed this when I was explaining how I did it, and I cannot put this in the initial condition, right? Like it has to be a global property if I want to just guarantee that n0 is bigger than 0. Here? Okay, so I could do this, right?
That wouldn't work either, I think, but you can try.
There is, what happens?
An _0 on the right.
Thank you. Yes, also doesn't work because this condition, it's not going into this case here of the implication. So I think what I would have to do is I would have to create a solver, add the condition globally, and then do what I want. Yeah, so I could do this, but let's choose not to, because if I did this, what I would get is such a counterexample, because it is the case that this property is not inductive. So what we do in this case is that we have to come up with an inductive invariant, so an invariant that respects these properties, that suffices to show the condition is invariant. So a way to do this is what we call a strengthening of P. So like I generate a new property that is inductive, and it suffices to show that P is the case. So rather than solving the problem directly for P, I solve the problem for this auxiliary property, and then that property is going to allow me to prove P. So this is what is commonly used when you are doing symbolic model checking. You come up like with such an invariant. There are many different ways in which you can come up with these invariants. You can use interpolation. You can use something like IC3, constraint Horner clause solving, and so on and so forth. You can try to strengthen the transition relation itself, or you can try to do something like K-induction that is going to unroll R up to a number of cases and then test the property also. So what is a problem in a scenario like this one, for example, is how do you come up with the invariant, right? So this is the other thing. How do you want to prove this property? There is another property potentially. I mean, there is going to be another property here that is inductive and that allows you to prove this other property, but how do you generate it? So this is one of the big problems of doing this sort of approach, which is generating the invariants that you are going to need to show that they are inductive and then that they are going to be sufficient to show the property. So, I mean, there are these different ways to do this, but there is also an approach that I want to mention that is based on SMT that you could use to generate the invariants. And so we're going to come back to this example in a bit to generate automatically the invariant that I could use to show that it is inductive and that it suffices to prove the property that I'm interested in. Okay? And the approach to do this is using synthesis. So you can think of like synthesizing these invariants as a program synthesis problem. So this is something that until what time do I have again? Okay. Right. So you can phrase the problem of generating invariant as a synthesis problem, and this is something that has found like usage together with SMT solving also. This is the very general problem of coming up with something that satisfies the specification, that has a large number of applications, as we well know. I mean, right now, like, people use a lot of large language models to do this for software and so on, but it's difficult to have guarantees about the results that you're going to have. So a little over 10 years ago, a new paradigm emerged to do this, which is what is called syntax-guided synthesis, where it was heavily based on SMT, in which you would phrase the semantics of what you want to synthesize should respect the specification of that as a formula. This is a second-order logic formula in which we're quantifying over this variable that is a function, but the property that you have here would be a first-order formula that you would phrase in an SMT theory of interest. And then the programs that you want to consider, so the possible values for f, would fit like such a grammar. And you can think of like an invariant synthesis to be done via syntax-guided synthesis exactly as finding the function over the state variables that respects these three properties here, right? First, that it's inductive, and then that it suffices to show that the property that you want to prove follows from it. Right. So here I have this is an extension of SMT-lib called synth-lib, where you can phrase a synthesis problem and then ask a solver that solves syntax-guided synthesis problem to synthesize what you are interested in. And in this case, we're going to use CVC5 because it also has the capability of doing synthesis. So here we are specifying this invariant, which is a predicate that operates over the state variables. I have here the initial conditions that I wrote with this wrong guy here, but like this is not going to make such a difference. I have the transition relation, and then I have the property. So it's the SMT formulation of the specification that we have for this, right? The initial conditions, the transition relation, and the property. And what suffices is to find a value for this invariant that respect these three things. So this is what I'm writing with these constraints, that the initial condition implies the invariant and the transition relation imply the invariant in the next state. So these two first guys here are going to show that the invariant is inductive, and then here that the invariant suffices to show that the property holds. And this check synth is similar to check sat, but rather than determine whether this is satisfiable, it is sort of doing that, but in second order logic, where being satisfiable is coming up with a value for inv that satisfies these constraints. And if I run this, CVC5 is going to give me this answer, which is hard to read. If I say this, it's going to be slightly less hard to read. But this is something that is an invariant that respects the properties. You had a question? Oh, right. That is, yeah, right. Where is the grammar? So, right. So you are not required to specify a grammar. And what happens is that when you are not required to specify a grammar, the system is free to come up with a grammar. So in this case, what CVC5 is doing is to come up with like conjunctions and disjunctions and negations of the variables that you have here to build the grammar. I mean, also, so it depends on the types, right? So you have integers and booleans. So CVC5, for example, has a default grammar for integers, a default grammar for booleans, and then for the combination with the predicates and so on.
So also related to that, is there anything, since you don't have access to the program, it's all now formulas, is there anything that you can do other than just searching for terms in the grammar, plugging them into the formula and checking, or is there anything more happening there?
So you sort of have access to the program via the transition relation, right? Sure. So this is encoding the semantics. So it's a combination of the two things. So you are enumerating. So the way that this is generally solved, like, is these enumerative SIGs counterexample guided inductive synthesis paradigm. This is how, so in this example, you would be enumerating a solution, it's failing, you get a counterexample, you test more until you succeed. So where the smart search comes from is in trying to leverage the specification to come up with counterexamples that can be general enough to rule out a huge space of the search space, a huge part of the search space. So this is where you are leveraging the program. It's by its encoding. However, I mean, there are, so this evolved, right? Like in CVC5, you do this by encoding to data types, and then you do a lot of stuff and so on. I'm not gonna detail this much. But it's in that part, when you're doing the search, that you are leveraging the specification to try to do smart things. So in the case of inductive invariant generation, for example, one work that we did at some point was to try to also use some machine learning techniques based on the counterexamples that you are showing to try to build a classifier of what are the bad states, the good states, the conditional states, and things like this. But you try as much as possible to leverage the semantics. Otherwise, it's just enumeration, as you said. So if we were to take this invariant and then write it in my program, and then I'm going to, so here, so what this formula here corresponds to is this, is that the inductive invariant is that C has to be bigger or equal than 1 and is smaller or equal than N. And this suffices to show the invariant, sorry, the original property. So I want now to generate the versions of the environment for both the state variables and the primed versions, and then prove that the invariant is inductive, which is these two first properties here, and then finally prove that the invariant suffices to show the property. And if I do this, it's going to succeed. Proved. So some SMT solvers can do it all, right? Like, but I mean, this is an alternative that you can do to solve this, but you can also apply the regular techniques. It's a matter of like how you come up with the environments that is important in this case. But the point is that the reasoning to SMT goes into several parts of this to test the validity of the property. In some cases, its inductiveness, and so on and so forth. Okay? All right. So I wanted to talk also about software verification. So the problem that you have here, it's like we did like with that thing with BV, that like you want to test a given property, you have no loops here, so it's great. You don't need to reason about invariants and so on. But you have to encode the semantics of the program into an SMT formula. And in this case that I have this C program here, like I need to reason about memory because I have these pointers and so on. And what is generally done is you can represent, for example, the heap as a big array indexed by the addresses of these variables as bit vectors, and then you have bit vectors as the values. And then you want to test, for example, this property here, right? So if we want to write an SMT formula that corresponds to the semantics of this program, it would correspond to the series of manipulations on the arrays and, of course, on the bit vector values that are stored here. So note that each one of these H's represent the state of the heap after the operations that I do here, right? So H0 is whatever state I had initially, then H1 is going to be where I am storing into A the addition of the value that I had before in A and the value that I had before in B. This is what I'm doing here, right? So the new heap is the heap I had before, where in the position indexed by the pointer with the address A, I'm going to get the value pointed by A and the value pointed by B added, and so on and so forth. So if I generate a formula corresponding to these operations, I have exactly this, right? So I'm creating all these arrays. So heap is the name I gave to this array sort that corresponds to the heap. I have these A and B, which are these bit vector values. And then I created here a solver. In this logic, ABV represents the combination of arrays and bit vectors, which is what I need to solve this problem. The constraints I have, they correspond to the variations that I generate of the heap after each one of the operations. And then finally, I add the negation of the property I want to show that is valid, right? The property that the value that I have at A in the end is the same as I had originally. No, this property is wrong. So I want to show that A is owed B and B is owed A. So this should have been B. Okay. So this is what I want to show, right? And if I ask my solver to do this, it's going to say that this is not a valid property. So the negation of it is not unsatisfiable, because with these values here, things break. This is sort of annoying to read, but like what this corresponds to is simply this, because I have aliasing happening here. So it's not the case that I can add, I can move A to B and B to A, which is what this swap was trying to do, but it's done wrong because I had to use like a temporary variable and I did not. So with this state of the heap, it would break, right? Like because I would get, in the end, different values of them than I wanted. Yes? It could also break because of overflow. Yes, that's true. Even if I had like the correct, no wait, is this true? Oh, because I'm adding, yeah.
Unless the type int is unbounded integers, it would, A plus B, star A plus star B could overflow as well. I thought that's what your example was showing, which is why I was surprised to see. The numbers seemed quite big, but I didn't know what it was.
No, but maybe you're right. Like, this example shows the aliasing, but like this maybe shows the overflow. Might be.
Yeah, that's why I thought the 0 was coming. Hard to read, sorry.
You may be right. Like, I must say I'm not certain. I'm not super confident to say no. But yes, like it's the kind of situation where things could break in different ways. Okay, so there are other applications that are similar to those. Contract-based software verification, it's very similar to what we're doing with model checking. I'm not going to go in detail into this, but like this is heavily used. Oops, what did I do? What? Well, it was not going back when I thought. Anyway, so this is when you have the same problem that you have the semantics of your program that you want to encode into SMT, and then if you have loops, you have to reason about invariants, you have to show properties. It's based on preconditions and postconditions, but in the end of the day, it's the very same idea that we had of symbolic model checking that is happening here. And there is heavy use of SMT solvers in this scenario. There are tools like Daphne that is used for writing programs that you can annotate with specifications that uses an encoding to SMT using the tool Boogie. It's very successful with Z3, for example. There is Verus also, which has been growing in popularity. It is used for doing verification of Rust programs, but there are similar tools based on other languages like Spark and so on. So but it's based on the same ideas that we said before. But you have to generate SMT forms that correspond to the checking that a given property holds after you have executed a number of instructions of the program. If you have loops, you have to be careful to have invariants to guarantee that you can reason about the property after an unbounded number of operations happening in the loop, and so on and so forth. Okay. There are other applications like scheduling. You generate a big arithmetic problem, try to come up with a solution. Since we can reason about arithmetic, this is a scenario in which you can solve this. So by the way, you can always use an approach like based on linear integer programming, but what it buys you to be able to also use SMT for this is that you have a general way of encoding problems, right? That if you have a combination of this problem with other things, then you suddenly can not have like a dedicated solution that it would not be able to be generalized to such other scenario. So for example, if you want to reason about scheduling time-sensitive networks where you have to encode these extra properties, like it can be very useful to use something based on SMT rather than having your own very, very complicated extension of an integer linear programming program. Yeah, and you can do like hybrid systems verification because you can reason about nonlinear arithmetic as well, and so on and so forth, as long as your SMT solver can handle this kind of stuff. But one thing I wanted to mention is automated compliance. So this is something that I mean the CVC5 team and colleagues, like we have been collaborating with others with Amazon specifically. So we had a CACM paper last year where we described the usage of proofs in this setting. I mean, very general, the production of proofs, but also in using for automated compliance. Because that example that I mentioned, like where they were doing analysis of access control policies, like AWS, it's saying to users, your policy is secure. It's not giving permission to these other people because an SMT solver said so, right? And to do this, you have to trust the SMT solver. But these systems, they can be very big, so it can be difficult to trust them in certain scenarios, especially if you have to convince auditors of this. So if you have, however, the production of certificates that are independently checkable from the system, that when it says that this policy is secure, it gives an independently checkable certificate that can be checked by a much simpler and much more trustworthy tool, then it can be helpful to automate the process of compliance rather than having to give a very manual and detailed justification for why you should trust the solver. You just rely on trusting the checking of the certificate. So this is a setting that we have gotten a lot of traction from, and this corresponds to our general interest of making SMT solvers more trustworthy and hopefully more understandable. Yeah, so to mention briefly about proofs and certificates, so as I mentioned, SMT solvers, it can be difficult to trust 300,000 lines of C++, even though we test them a lot. We have several good software engineering techniques for this, but still some things are going to remain. And also in certain scenarios, no amount of trust based on that is going to be sufficient, so you do have to have independently checkable certificates. And it can be too costly to certify the solver itself to prove the code correct, for example, because that is not only hard, expensive, but also freezes the code. So you will be very resistant to change your code once you are going to have to certify it again to be able to use in these settings afterwards. So one approach that is more common is to have the solvers be certifying, which is for them to produce certificates of each result they produce that can be independently checked. And then you decouple confidence from the implementation, which is the goal here. But there are, however, of course, challenges to this, which is why it's not the case that every SMT solver is proof producing. And so this is a list that covers a lot of stuff. So it's difficult to collect the information necessary to do this efficiently, not only as a matter of just how much it's going to slow down the solver, but just being able to track everything. The system is very big, it does a lot of stuff, and you have to reasonably track everything that is done such that you can have the certificate afterwards. There are some techniques that are very difficult to be producing from. There are some theories that it's not even well understood how you would represent the reasoning in a way that can be efficiently checked or efficiently produced. A proof would be efficiently produced. There is no consensus on a standard proof format. This is something we're trying to achieve, but it takes a while. And also how you're going to do the scalable trustworthy proof checking afterwards. But yeah, we have tried to address this to the best of our abilities. We have achieved some success. We're continue working on this. But we are doing this trying to with some goals in mind, right? We want to produce proofs in different formats such that usability can be increased by people who need proofs in different formats or with different levels of granularity. Also, there is a mix of tracking everything the solver does during solving This is what we call eager proof generation versus leaving some parts of the proof to be elaborated only afterwards because it was too difficult or too inefficient to record the details during solving. Yeah, so this goes into it. So this picture, I'm just going to show the end of it. So yeah, so like, oops. In an SMT solver, you have all these reasoning components, like at a high level. So you have a SAT solver that is reasoning on Boolean abstraction. You have a classification. You have a preprocessor that is simplifying the formula. You have a theory combination of all the different theory reasoning procedures. And these things are communicating, and all of this has to be made proof-producing. So the big challenge in doing proofs for SMT solvers is that you have to instrument all of this in a reasonable way while maintaining all of these requirements of being very efficient, having proper output, and so on and so forth. So this can be very challenging, but the proof that you get in the end is going to be a combination of all these different kinds of reasonings. And to have a little understanding of a proof, let's look not at like a proof like the ones I was showing before, but like a simpler problem. So the proof is a bit smaller. So let's say that I have this little problem here, okay? It's just a combination of Boolean reasoning, inequality, and function reasoning. So this is in the quantifier-free uninterpreted functions logic. And yes. So for this, I'm going to use CVC5's binary. And this is the, the problem, as I had before, right? So if I use dump proofs, this is the command. So if I had written this as a Python program, I could use that dot proof thing if I had set the options to produce proof. But if I'm using the binary, I can just pass this command, and CVC5 is going to give me a proof. So this proof here is in what is called the CPC format. So we have two main formats nowadays in CVC5, which is this and this other one here. Yeah, and the proofs are of similar size, like the changes are small, like, but the point is that you have conclusions that are the result of inference rules. And to understand what a proof like this looks like, you need to understand these rules, right? So we have a specification of CVC5's proof system. So if you go in the CVC5 website, this is bad. And then proof production, proof rules. And then here, there is a high-level specification of the proof format of CVC5, of the rules of inference the system uses. So like in that output that we're getting out of the Python API, it was using directly this representation here is just as expressions. The thing is that there are hundreds and hundreds of rules, right? Because there is like a lot that the solver is doing. Yeah, there is a lot of simplifications, there is a lot of rules. But when you get a proof out of the solver, you can have a checker that is implementing the semantics of these rules, and then you can check them. You would now have to trust a checker, right? So in these two formats that I mentioned here, CPC, it is based on a language called Eunoia, and this ALET. We have efficient checkers to check these proofs, like, but they are each between like 5,000 and 10,000 lines of C++ or Rust. So you still have a large piece of software to trust, even though it's much smaller than 300,000 lines of like C++ of CVC5. But what you can do is to go into proof assistance, for example, if you want utmost trust. So this is something that we're actively working on also. So we have connections of CVC5 working now, both with like Lean4 and Isabelle Hall, such that you can check CVC5 proofs in the systems. There has been also, with this format, ALET that CVC5 produces proofs for, connection both with Isabelle and Coq. And what you can get is that if your goal is to have utmost trust in the rules, you can go into these systems. But you can also use CVC5 as an auxiliary tool to solve problems from these systems. If you encode your the checking of a given theorem into the language of CVC5, because it can give you a proof that can be converted into a proof in the logic of these systems. So this is what you can get with this sort of approaches also. So that's what I wanted to talk to you guys about. I hope you enjoyed it. Thank you very much. Any further questions?
I have a small curiosity about your example of Amazon. So I'm a user of Amazon. I'm denied access. What is the feedback I get back from all the things that you have shown us? Just access denied, or?
All right. So like the use case is not exactly whether you as a user would give access or not. Is as a manager of resources, whether you would give, and then you have a set of users of your service, for example, and then you want to give access only to some of them for some resources. So as a user itself, you would never see this, but as the manager, you would not unwittingly give access to some people who should not. And this tool would prevent you from doing this. This is how it would work.
So manager, basically, they don't need explanation.
So they just get the explanation that your access policy gives more rights than you wanted to give. I do not know like whether their interface can give more information than that. I don't know. I think
There are tools like Gurobi. How do you compare this SMT-like solving, what they do, and sometimes the performance is strangely different, and how do you compare them in general?
Right. So the first big difference is that a tool like Gurobi is going to use floats when reasoning about the representation of your numbers, which means that it's not generally going to be exact, so it can have errors in computations. So this allows you to be much faster, but you do not get exact arithmetic. So this is one thing that SMT solvers are way behind in terms of performance because of that, because they want always to be precise. That's one thing. But moreover, there has been much more extensive research into making a tool like Gurobi more efficient than the arithmetic procedures that are used in CVC5, for example. CVC5 uses simplex, for example. So it is not incredibly efficient in solving the sorts of integer problems that you would have. However, its effectiveness comes when you are thinking for problems that you have the combinations.
Can you comment on the nonlinear behavior? And second, is there a study comparing SMT solver and Gurobi-like tools?
So for Gurobi specifically, I cannot say, but but to give you an example, like if you want to do neural network verification, right, that you have to reason about very, very big problems, then it can be very difficult to apply exact methods because they're not going to scale as well as the implementations that are not exact. So in that setting, people are often giving up on having exactness because they would not scale otherwise. So this is sort of like a study that happened in the sense that people have tried to use SMT solvers. They could not use it directly. So they had to rely on systems that are not exact, even if they would employ some of the logic reasoning techniques. Because you do have like this is a number that's sort of folklore, but my understanding is have like a 3 order of magnitude slowdown just by not using floats when you want to do the arithmetic computations. Also, there have been works on trying to combine both systems in that you would reason in an inexact manner using a system like Gurobi, for example, get a solution that you would try then to transform into an exact solution. There has been work also in what's called delta satisfiability, which is that you can try to give formal guarantees of the inexactness of your integer reasoning. Yeah. more questions? I think you had a question.
Yeah, I have a feeling about the certificate part that you presented at the very end. In most cases, these proofs are going to be huge. Like you say, easy to check. Yeah, I mean, in terms of each individual step, but they're going to be really, really big. Like, and sometimes, like, what's the use of this? You can automatically check that every step was correct.
Yes.
But it's going to be completely unreadable and giving you no insight as a human being on why things work. So it's far from explainability, right? So it's if you go to people that do COC proofs of actual systems or lean proofs of actual systems, they tell you that the important thing is not that you finish the proof and it's checkable. The really, really important thing is that you make all the assumptions explicit, because this is going to be the attack surface of a system from the point of view of the attackers or the bugs, right? In the sense that the attacks are going to be violations of the assumptions, not actually exploiting incorrectness implicitly or explicitly of the system, right? And this is something that probably you don't get that easily by these certificates if they are unreadable.
Yeah, so there are a few aspects to this. So like to comment on the case of the proof assistance, the goal here is not that you would get like your big mathematical theorem solved directly by this with an inscrutable proof that like you could not leverage for anything other than check. So the use case in proof assistance, for example, is generally that in the middle of the proof you have several dumb steps that like for you as an experienced user of a proof assistant are just tedious to do, but they can be automated away with a tool like this, with an SMT solver. So this is what people use this a lot for. In Isabel, for example, like that is a common understanding that like this makes a huge difference in the speed in which you can do formalizations by just shoving the tedious stuff to be done by the automatic tool. But you are still building like a proof like that is structured, that can be leveraged for several things, as you said, like to have an understanding of why that actually holds and what is it that you are proving, and so on and so forth. But for a scenario like this one of automated compliance, this is really about correctness. So you are giving an answer that has to be trusted. You assume you already trust the rest. You trust that like the way that I have encoded what the answer means when converting to SMT is something else. But the problem here is, can I trust the system that is telling me that this logical formula is valid? And you are just outsourcing the trust from the system that is very big and difficult to trust conceptually to a system that is smaller and can be trusted more easily. So this is what is happening here. And then going like one order of magnitude down in terms of the system, lines of code of the system you have to analyze is already something. And then if you can go even further down by going to proof assistant, it would be even higher level of trust. He had a...
So one question about trust is the meta theory. Have you made any attempts to just verify the soundness of the meta theory, the proof rules that you have?
Yes, so the cool thing also about when you go to a proof assistant is that you have to do this. You have to, I mean, if you want to use it also for generating a proof of a theorem inside the proof assistant out of your proof from the solver. So you have to formalize the meta theory also. So in our work, both in Isabel and Link4, this is what we are doing. So we have formalized the meta theory of like quality and interpreted functions, arithmetic, bit vectors. There is some work towards nonlinear, finite fields, and so on and so forth. Because you need it if you want to have, in whatever theory you want to produce proofs for, that you want to embed into the systems, you have to do it. That is also, even if you did not want to do this, that is the benefit of having confidence on the correctness of your calculus anyway, also.
So one question I had about that is, how do you then work with proof combinations? Do you formalize that in Lean and prove the soundness of theory combinations when you work across theories?
Yeah, so the nice thing is that you don't really need to, because the way that you represent the proofs of theory combination is rather simple. So if you take a framework like Nelson Open, what is happening there, this is a framework that is used to get the reasoning out of a theory, the information from that to the other theory. This is shared via equalities. So it's equalities among the symbols that are shared between the theories. So you just have to justify why that equality holds. And this equality holding is going to be based on the reasoning of that particular theory. So you do not need to argue about anything of the correctness of the theory combination method. It's just that in that instance of theory combination, was it done correct? And whether it was done correct depends only on the theory reasoning. This is a nice thing of these proofs. It's that like it doesn't matter often how you are solving the problem and so on. It's a matter of like how you are representing the reasoning that happens. For arithmetic, this is also linear. You just need to represent that like the validity of a given formula in linear arithmetic comes from a linear combination of the inequalities. You do not need to reason how you actually came up with the coefficients of that combination. It's just to have them. If we don't have more questions, I think we can end. Yeah. Thank you very much.